Okay, welcome to track 25, everyone, where we have a broad spectrum of speakers and subjects, from the macroeconomic to the technical. We're going to give our speakers 20 minutes each. I'm going to ring the bell after about 17, so they've got a warning of about 3 minutes. And we're going to take individual questions at the end of each presentation. Our first speaker is Mark Dannettel, which soon we'll introduce.
Good afternoon, my name is Sunu Kwan. Let me introduce first presenter, Mr. Mark Dannettel. He is a vice president with Thornton Tomassetti, and currently serves as the regional leader for building skin services in the Pacific Rim and the western region of USA. Mark has also been very involved with architectural education. He taught architecture at several universities, such as Chiang Mai University in Thailand, Chinese University in Hong Kong, UCLA, Arizona State University, and Southern California Institute of Architecture. Please welcome Mark Dannettel.
Normally I finish my slides the night before, but this time I finished them nearly a week ago. So hopefully I don't forget everything. For starters, I'll just say that Thornton Tomassetti is a multidisciplinary firm. We have 5 principal areas of practice, being building structure, building skin, building performance, which deals with existing buildings, property loss, which has to do with property loss, and then construction support services, which I also get involved with for the building skin stuff. And we're also located internationally around the world. Last time I counted, it was 18 offices. Might be more than that. Whenever I present, I have a problem with the pronoun we. I say we all the time, but we could be anything. It could be Thornton Tomassetti, as I'm an employee of TT now. It could be the building skin practice within Thornton Tomassetti. It could be my previous employer, ASI, which was a contractor, because much of what I show is from my work as a contractor, especially when I talk about cable nets. Or it could be the specific project teams. If I'm talking about the Loyola project, I could be talking about SCB architects together with the consultants and myself. Or it could just be talking about the building industry as far as consulting industry for facades. It could be any of those. So I try to be specific when I can, but it's a big group, and I identify with all of those groups. And then lastly, this is not specifically about Thornton Tomassetti projects. This is about the topic of building skins, which are supported by cables. So I'll be showing jobs that I completed while I was with ASI as a design-build contractor. The 3 buildings are really the Qualcomm building by Delaware Wilkes, Rodriguez, and Barker, and then the museum by Polshek, and then finally the Loyola University job by Solomon, Cordwell, and Benz. This is what I was hoping to talk about. I don't think we'll have time to cover all of this. But one, I want to talk about the variety of forms that are available with cable-supported systems. Then I want to talk about the types of systems there are. We want to talk about some engineering issues, especially just boundary conditions. And then ideally, we'd like to talk about some of the required components as well as installation issues. Okay, so forms that are available. You can do them flat and vertical. It's nice and simple. Or you can do them flat and sloped, but flat and sloped you would think is the same, but it's not. I'm not used to using a microphone because I need to stand in front of you, so I'm going to shout a little bit. When you have a flat building, a flat facade hung with cables, it just wants to hang straight. But as soon as you want to slope it and lean it back, now it wants to hang like a wet towel. So the middle wants to sag. So when you work with these kind of systems, now you have to engineer and detail in a series of props so that all of the points actually push the glass out into a spherical pattern. But when you add the glass weight on, it actually deflects back into be a flat form again. So this is a lot more complicated than it looks. You can also do cylindrical shapes, whether you're putting the framing to the inside or to the outside. Again, you can do conical shapes, which are sloped cylinders. And again, you have the same problem of the wet towel, so you have to prop everything forward again. And then you can do dome shapes, hemispheres. And hemispheres aren't always hemispheres. Sometimes spherical forms are just kind of a lens, which may just be the top of a hemisphere. And then lastly, we have something called anti-clastic. Anti-clastic is not the opposite of clastic. Anti-clastic is the opposite of something called synclastic. And what it means is that the curves that generate the form, the radius for those curves are on opposing sides of the form. So if we look here at the horizontal, this curve is concave, facing out towards all of you. But the vertical curve here is convex, facing back into the building. So the form is generated by two sets of curves, but from opposing sides of the form. And again, here, this is a synclastic or anti-clastic dome, and it's more commonly called a potato chip or a saddle shape. This is a fantastic example, SeaTac Airport, of an anti-clastic wall. It's basically just a cylinder form, which then there was a series of cables that run horizontally, and when you pull those horizontal cables, essentially what they're doing is it's like putting on a girdle, right? You start maybe just vertical and flat, but when you pull them tight, now it pulls in the middle, and it creates this anti-clastic form. So really, this is just generated by the two cables pulling against each other. The horizontal cables are pulling around the building, which is curved, and the vertical cables just want to take a straight line. But because of the horizontal cables, they actually pull in. Like that. Okay, so now let's talk about systems. We have cable nets, and this is actually a cable net. I only refer to these as cable nets. This means that we've got two sets of cables, one running horizontal, one running vertical. It's a true net, if you will. You can do anti-clastic forms with cable nets. This has two cables running both directions. This is pairs of cables, though, so I don't call this a cable net. So if you see here, there's pairs of cables running horizontally, and then there's stainless steel hanger bars, which take the dead load of the system. So it's very similar to being a cable net, because if it was a cable net, we would have a vertical cable here and one horizontal. But since we lost that one vertical cable that's no longer acting in tension, we basically had to take that vertical cable and turn it horizontal and add it here, because we still have the same structural requirements. We still need the same amount of tension in the system. So another example of horizontal cable pairs, again with a steel system being the suspension or support for dead load. So then the next system would be cable trusses. And cable trusses have cables which basically oppose each other. This is very similar to the anti-clastic cable net, where basically you've got one set of cables pulling down on the skylight, and you've got another set of cables that are pulling up on the skylight. And basically they resist each other, and they resist positive and negative wind loads. These are more cable trusses. There you can see the horizontal cable truss. And these are the struts that you use in order to keep those cables opposing each other. So this is a cable truss in plan view, maybe. And the way they work is that you tension the ends, and then that puts the cables in tension. And then they remain pre-tensioned like that for the life of the job. But now we apply wind load, and basically the wind load transfers through those front struts, and they apply it to the back cable. But if we apply negative wind load, then it works the opposite. Now it's pulling on the back cable or front cable. Depends how you look at it. So, as an option, you can pull those two cables apart. They're still the same diagram. Or you can move them to the back. And again, it's still the same diagram. It's just that you've moved the positions of the cables. The loading still works the same. Except here, I'm not attached to the columns, so it's an obvious problem, right? So this is a job where we're supporting ETFE with cables. And so what I've done is I've drawn in, you can see the cables running back here. You can see all of these. They look like they're just sagging from self-weight, But actually what you don't see is there's another cable below them that's pulling the system down and keeping it tight and rigid. This is Bangkok International Airport. This is a mast system where we basically have a compression mast which goes down the middle of the system, and then we have a cable in the front and a cable in the back, which is doing the same thing as what we were doing in the cable truss, except instead of pulling on the structure itself, the columns at each ends, now we're putting all this load into this compression strut. So we're actually isolating all of the cable loads to go up and then get to the top and then come all the way back down through the compression strut again. So it's kind of a self-contained tension system. But if you look carefully, we also have tension trusses in here as well. They go side to side. This is another mast system. So you can see the front and back cables and the mast in the middle. This was a hybrid system that I developed for a project in California. Basically, we have the masts. So we have a series of vertical masts, but they only have the rear cable. So what do we do about the front cable that's missing? There should be a front cable here that's putting load from the outside in order to keep the system balanced. So what we do is, it's already a curved facade anyway. So we just use the horizontal cables that run directly behind the glass, and we tension them from each end. And basically that's helping to pull in the facade, whereas these vertical cables here are pushing out. So it's a hybrid system. So there's the horizontal cables being activated to resist the vertical cables. Okay, so let's talk about engineering and some of the boundary conditions that we need. There's a lot of load in these, and I meant to print myself a cheat sheet so I could tell you how much load, because I don't keep this in my head. Maybe 30,000 pounds would be common to have in these cables for pretension. So what do we need? Well, that's what you need. You need a very big truss up here at the top to take the tension load of these vertical cables. And then you also needed concrete piers or concrete decks on the left and the right in order to take the horizontal loads. This is that vertical truss at the top. That vertical truss is not doing anything other than just taking those cable loads. So, frequently we're asked to do cable structures where there's really no provision of structure. And we have to tell, the designers or the clients, look, I'm sorry, the way that the building is right now, you really don't have the capacity to take the cable loads. This is one of the 3 jobs that I actually built as a contractor. This is where the horizontal cables are located. And that's what's resisting the cable loads. We have massive concrete piers at the left and right ends of the building, giant bookends. So what about the Qualcomm project, another one that I built? That's the horizontal pairs of cables, but it doesn't look like there's much resisting these over here, right? There's no big structure at the left and right. But if you notice carefully, there's no cables here. Why? Because there's no structure there. This top set of cables comes all the way across here and ties right into a floor deck. And if you look carefully, you can see the drag beam, which is actually pulling this force and dispersing it back into the building. And if we keep going floor by floor, you realize all of the cables are tied into the floor decks, and the floor decks act as diaphragms to carry these loads back into the building. Okay, so components. We have cables. They're pretty important for cable-supported walls. But there's 3 kinds. We only use 2 of them, really. This is known as strand, is what we most commonly call it. Here they say it's spiral rope, but we never call it that. We call this strand. This is one set of wires which are basically revolving around a central wire. Then we have fully locked cables, which more or less have a conventional set of wires in the middle, and then the outside is a series of die-formed wires which interlock carefully. And then here at the bottom we have what we call rope. Rope is more commonly used for elevators because it's much more flexible. It's also used for other structures where flexibility is required. But mostly for the jobs that we do, we're either using strand or we're using the fully locked cable. Fully locked cable is a lot more expensive, so we tend to not use that. So usually we're doing this. This is what it looks like when it's in a box. This looks like it's spaghetti laying in a box. It looks very lightweight and simple, but actually these are very heavy ropes. This is probably 28 millimeter rope, so it's 1.25 inches or 1.1 inches. And then pay attention, this short little one here, I'll show you this one a little bit later. Every time that, as a contractor, we ordered a set of long ropes here that we were going to use on a job, we also order a short one for testing. But it's exactly the same construction, same strand, and same end fittings. This is, if we back up for a second, this end fitting here is called a swaged fitting. There's a series of tapped threads here that are cut, and then we've got the basic swage, which this rope or strand cable comes inside the swage. So I'm going to shout at you again. So the way this works is the threaded portion is here. It's tapped into a solid block, and from the left side that we can't see over here, we've got the cable, and we bring this cable and we drop it into this hollow sleeve, if you will. But then this wheel here and this wheel down below, these are very large hydraulic rams, which basically press together on this hollow tube, and then by grabbing it here, they actually pull the hollow tube through the rollers. And you can see the deformation of the stainless steel sleeve here. So basically what's happening is they're just taking this hollow sleeve and squeezing it onto the strand rope. That's important from an engineering standpoint to know that you're dealing with something that's been squeezed onto the rope. Because basically the failure of mechanism for those kind of fittings means that the rope will actually pull out of that sleeve before the rope itself will fail. So there's always a 0.9 factor whenever you're using those kind of ropes or those kind of end fittings. Those are called swage fittings. So they differ from something like a spelter socket. A spelter socket is shaped like a funnel. You put the cable through, then you pull it apart, and then you put grout inside, and then it cannot pull back through the funnel-shaped fitting. Whenever we do cable systems, we always have castings, almost always. These are called investment castings. Basically what we do is we have a die form that we inject wax into, and for every casting that we need on the job, we have to make one piece of wax. So what we've made here is a clamp. Using these two die forms together, we injected this wax in there to create this one clamp shape. But you can see this little nib here. This is where the wax was coming in. So now all of these ladies here are basically taking this piece, cutting off the injection point, and then they're actually tapping on these other pieces which create the flow tunnels for the stainless steel to enter into the hollow void later. So we start with a solid wax, and then they dip that solid wax into powder, which is basically ceramic dust. And you can see here, these are castings that have been coated with the powder dust. They've been coated many, many times. They have a thick layer on them. So that's ceramic. And then basically, we take that ceramic and we put it into an oven and we fire it. And so now it becomes a ceramic shell, and all of the wax is drained out because it was hot. So now we take that ceramic shell and we pour stainless steel back into it, and these are the castings that were actually made for that Qualcomm project. Then we have to take them through a non-destructive testing process. Here, unfortunately, you can see the word rejected underneath the ruler, and this is why it's rejected. All of these stains are residual dye, which is residing in some kind of crevices and cracks within the die. So now they have to send these back. They have to drill out the defects. Then they have to weld in stainless steel material. They have to regrind it. They have to re-sandblast it, and then take it back to NDT testing again. It's a very long, arduous process to deal with castings. Then once you've got that, then you've got to machine them. This guy is checking for the precision of the casting so he can put it in his CNC equipment. Once he gets it in the CNC equipment, if it doesn't register properly, he can't drill on it properly. So if they don't register properly, then we have to send them back out before he machines them. We have to reheat them, and then we take a hydraulic press here and we ram it down and flatten the casting so it's not warped. So then he can work on them again. That's what it's supposed to look like when we're finished. This is the testing I was talking about with the short cable piece. We actually use this to calibrate this equipment, which we use on site for checking our tensions. It's called a tension meter. So we first pull it to the correct load. We calibrate this tension meter so we can use it on site. Then we remove the tension meter, and then we go ahead and pull the cable until it breaks, and we verify what load it actually broke at in order to confirm our engineering. Then sometimes there's pre-assembly in the shop where we actually pull sets of cables together and we preload the clamps. We actually design the spreader bars here for lifting the clamps, and this spreader bar will actually be sent to the site in order to install. This is us putting it on the truck. Here's the spreader bar I was talking about. Here's the compressors. Here's the spreader bar again being used on site in order to lift the cables. These are the cables here. You can see the guy's got a pair of cables which he's going to load into the floor deck here. This is him loading it into the floor deck and trying to make the connections. And then finally doing the jacking equipment. These are called jacking chairs, which we design as well. Attaching the hydraulics. In this case, the entire cable net was pre-assembled and then hung like a big drape. Here you can see a big spreader bar at the top. Some more samples of jacking equipment that we have to design and engineer as part of our design process. And then this is the finished wall for one of them.
Mark, would you finalize your presentation?
This is done.
Okay.
Thank you.
Thank you, Mark. If you just wait there, if you wouldn't mind, for questions. That was incredibly informative. I now know what anti-clastic means, and that was very, very useful. Have we got any questions for Mark, please? Because if we haven't, I've certainly got one or two. Anyone? Okay, well, I'm going to kick off. I've actually got a couple of questions, Mark, and your answer might well be related to both of them. I just wondered, as a designer, what gives you the biggest headache? And also, what are the situations and areas that these sort of systems are being used in now that perhaps wasn't the case 2 or 3 years ago?
Yeah, so actually, that was one of the reasons that I proposed this talk for CTBUH is I've been working on several high-rises recently where people have been trying to propose cable net systems quite high up on the building. And the difficulty is in trying to get the structural provision that can resist the cable loads that we need. Especially in a place like Shenzhen or Hong Kong where the wind loads are extremely high, the amount of pretension that we need in the cables is just enormous. The higher up in the building we go, the higher the loads go, but also typically the less structure that we have from the building in order to tie into. So that's certainly one of the points of the lecture is to try to emphasize that idea of needing those structural provisions.
Okay, any more questions? Yes? Bill.
Just wondering about the installation. Do you find it challenging to find good installers of these systems since they're so unique and specialized?
Yeah, it's a good question. I mean, while I was doing these jobs, I was actually the contractor, part of the contracting team. And we installed them with typical steel workers in the US. But that team that we used actually had prior experience with doing some cables. So the important thing was really having kind of our design and engineering support on site. I spent a lot of time on site for all 3 of those cable projects, making sure, like even the last one, I didn't really show enough images about it, but the Loyola project, they were pulling all the cables and the steel workers had instructions on what tension to take them to, and they were using the tension meter, and I happened to be on site and I looked at the end of the cable terminations and they were probably about 2 or 3 inches beyond where they were supposed to be. They were very close up against the precast, and as soon as I saw that I knew it was wrong. And I said, guys, stop jacking the cables, something's wrong. And they said, no, look, the tension meter's reading this, it's still not enough tension. And I said, no, you gotta relax. I don't care what schedule you're on. If it's over tensioned, you have to stop. And so we went back and actually took compression readings from the compressor itself, and multiplied it by the bore area on the jacks and realized, yeah, we were way over tension. So actually the tension meter was reading incorrectly because it hadn't been calibrated properly at the lab. So yeah, it's very important to have the design and engineering support on site. So it's always easy to find contractors that say that they can do it, but you really have to push hard to quiz them and make sure that they're really going to have the right know-how on site.
Okay, thank you, Mark. Let's give him a big hand.
Okay, we're now ready for our next speaker, who